All right, so we're going to talk about the potential energy of a point charge because of another point charge. Now, we defined in this last video electric potential as a location, describing a location in space around some other charge, as the potential energy a point charge would have divided by its point charge. Totally true. We can say that the potential energy a single point charge has as the charge times the value of the electric potential where the charge is located. But that's not particularly helpful yet because we don't know V either. So we do need to derive this. Let's say we have two positive charges, a Q1 and a Q2, and they are a distance of our initial apart. I'm using R because we've already talked about, for example, the electric force that one feels or experiences because of the other. Depends upon our constant K, it depends upon both charges, and then it depends on R, that denominator R represented the radial distance between them. And so I'm just labeling this as our initial. Since these are both positive, we know that they will be repelling each other. Let's talk about the work done on Q2 because of this electric force that it experiences. Now, yes, Q1 is also experiencing an electric force, but we can only talk about one of them at a time. So that electric force is going to make it so that eventually Q2 is at some farther distance away. So, and it wouldn't stop there, of course. It would keep moving because it's still repelled. I'm going to call this an R final. And it's still, of course, experiencing electric force. This electric force is just weaker because this charge is farther away. The reason I mention work is because we know work is the integral of force dotted with displacement, but because electric force is conservative, meaning the work done doesn't depend upon path taken, it just depends on initially where the charges are and finally where the charge is at. So we can equate that work to the negative change in potential energy as well. Now, we talked potential energy in the previous video, but that was specific to a uniform electric field. That is not the case here. Here, the force changes as these charges get farther apart. The electric field that Q1 is creating is getting weaker as well as Q2 gets farther away. So since the force is varying, we do need to integrate. So work is the integral. Our force, we already know, equation-wise, is K Q1 Q2 over R squared. We know that force in my picture is directly to the right. We know the force is radially away from Q1 because they are repelled. So when I think about the dot product, work is only done while the force and displacement are parallel, which that's how I've drawn it, right? Because I know if the force that Q2 is experiencing is to the right, it's going to move to the right. And so we end up incrementally needing to add up this little DS's. I'm going to call ds dr though, because it is this radial distance that is changing R is varying, which means that's the variable I'm going to integrate. So when I come back to my equation, the force and the dr I'm working with are parallel. So I'm just calling this ds dr. I've already accounted for the force and displacement being in the same direction. The limits will be from R initial to R final. It's whatever our variable is changing between. Excuse me. K is a constant. Our charges are also constant. Excuse me, so I'm going to pull that out. That leaves me with 1 over r squared dr. Okay. Now, let's continue it over here first. So K, Q1, Q2. Integral of 1 over r squared is negative 1 over r. So when I put in my limits, I'm getting negative negative K, Q1, Q2 over R final minus a negative, so that ends up adding K, Q1, Q2 over R initial. Now, again, I can equate this to the negative change in potential energy. So the negative change is final minus initial for the potential energy. Now, in order to say the potential, or I should say determine the potential energy of Q2 at a specific location, we need to know the potential energy at another location. Because right now we only have this difference. So, if our final, let's say Q2 keeps moving completely off the screen, it goes as far away as it possibly can. So if Q2 gets very far away, essentially our final being infinitely large, do we expect it to feel a push anymore? Well, no. So we're going to say the potential energy of Q2 is 0 when our final is infinitely large. Saying the potential energy is 0 is simply just saying there's no attraction or repulsion. They don't have, Q2 does no longer feels an effect from Q1. So if our final, if we put in infinity, well, that makes this whole term go to 0. We're defining the energy at that point to be 0 as well. So what this shows us is K, Q1, oops. K, Q1, Q2 over R initial is, these negative signs cancel, it is that initial potential energy. So we can now generically say the electric potential energy a point charge experiences because it is near another point charge depends on our constant. This is still the 1 over 4 pi epsilon naught. It depends upon both charges and how far away they are from each other. This determines the potential energy of one charge due to another. They both specifically have to be point charges, though. Or if you recall the force and electric field of outside of a sphere was the same as a point charge. This will work for 2 spheres of charge as well. But R has to be measured middle to middle. Or I should say center to center. That's probably a better way to say that. Okay. So let's say we have a 4 nanocoulomb charge that is positive and a positive 2 nanocoulomb charge, and they're a distance of 3 centimeters apart. The energy we can calculate. So plugging in our values. K is the same constant we were working with before. Our 2 charges, the 4 and the 2. The R needs to be in meters. Notice it's not squared. I almost squared it. We're so used to having the squared in the denominator, but it is not squared anymore. Energy is a scalar too. There's no direction associated with this, which is actually quite nice. Getting my calculator in scientific mode so I don't have to write decimal places. So I'm getting 2.4. Technically, I really only have 1 sig fig, so essentially 2. Now the units, I have coulombs squared here, which are going to cancel with both of my coulombs. The meter and the denominator is canceling with 1 in the meters. So we have Newton times meter, which if you recall, that is a joule. So the electric potential energy of these 2 charges would be 2.4 times 10 to the negative 6 joules. Let's suppose we change one of them to be negative 4 nanocoulombs. The other one's still positive. And they're still 3 centimeters apart. When we set up the energy, we have the same constant, but now we have a negative charge, which I am putting in. I'll leave my units off this time. When I did problems with force and electric field, I typically put in just the magnitude of the charge, because I knew I needed to account for the direction, and it just was easier to find the magnitude of the force or the magnitude of the electric field to find the direction after the fact. Here, because energy is not a scalar, it is not a vector, it is a scalar, there's no direction associated with it. So we don't end up with like a positive x direction or a negative x direction. We get a negative value though, which can be a little weird. We saw negative potential energies when we looked at the universal law of gravitation. Negative potential energy essentially means these 2 charges are bound. They're attractive. They're not going to escape each other. They're not going to push each other away. They want to get even closer together. So it means it's a bound system, which essentially is an attractive force holding them together. And instead of trying to push each other apart, like we would see in the case of having both positive. Now, mind you, if these charges were both negative, we would get a positive answer, because we would put a negative for Q1 and a negative for Q2, which in turn would give us a positive potential energy, which means that they are repelling, they're going to push each other away and essentially escape from each other. They're not bound. All right, so this potential energy also works if we have a system of charges, meaning more than two charges. So let's say we have our 4 nanocoulomb charge, I don't even remember what it was 2. Let's go ahead and just change it up though. 3 nanocoulombs charge, negative 5 nanocoulomb charge, and negative 1 nanocoulomb charge. Let's say they are on the corners of a square. That's 2 centimeters on a side. And we want to know the potential energy of the system. Okay, we know the potential energy, the electric potential energy of any 1 point charge due to another is kq over r. To find the energy of a whole system, we simply need to find the energy due to each combination. So let's call this Q1, Q2, Q3, and Q4. What I have to do is I have to find this energy because of the combination of Q1 and 2. But I need to add to that the combination of Q1 and Q3. And these R's are the same, but I will want to specify. I don't have a good way to do that. I'm going to call it A and B. I'll just use a letter instead. And we'll talk about it as we set up. Okay, so I have accounted for Q1 and Q2, Q1 and Q3, Q1 and Q4. But now I need to account for Q2 and Q3 and Q2 and Q4 and Q3 and 4. So now I have every combination accounted for. And this looks rather terrible, but it's not. These are all just going to be individual numbers. There are no vectors. That's the beauty of energy. No vectors. There's no such thing as the x direction or y direction when we talk energy. These R's are not all going to be different either. I'm going to factor out the K, because that is in every term. So our first term is our 4 nano. I'm going to leave them as nano just to save space on the page, on the screen. But when I plug these in, I will be putting 10 to the negative 9 in for them. So Q1 and Q2. The R in the denominator is the distance between these two charges. So coming back to my picture, Q1 and Q2 are a distance of 2 centimeters, which I do want in meters for my units to work out. Okay. Next one, Q1 and Q3, and I do want the negative sign. That matters. So Q1 and Q3 are also 2 centimeters apart. Okay, the third one, Q1 and Q4. This R needs to be this straight line distance between the two of them. So this is the R sub C, which of course we can get from the Pythagorean theorem. So 0.028. And keep a few decimal places. Rounding errors can make a big difference in these. Okay, so I've done 1, 2, and 3. The next one is Q2, so 3 nanocoulombs times Q3, negative 5 nanocoulombs. 2 and 3 are also this RC we just found. It's the same dimension, just the other diagonal. Okay, that's the fourth one. Q2 and Q4. I'm still going to run out of space. 2 and 4, this distance is 2 centimeters. And then the last combination, 3 and 4. So charges 3 and 4 are also 2 centimeters apart. So now it's a matter of plugging and chugging. I'm going to pause the video too, since it's going to take me a minute to type this all in. I'll be back. All right, so I ran through this a couple times to make sure I was continuing to get the same answer. The answer I'm getting is negative 8.7 times 10 to the negative 6, and it will be in joules. To see that, the K value is newtons meters squared over coulombs squared. Each of these inner terms, because I did put in 10 to the negative 9 for nano for all of them, I have coulombs squared over meters. So the coulomb squared cancels and one of the meters cancels. As a reminder, a newton times a meter is a joule. So the energy, the total electric potential energy of all of these together is negative, meaning it's a bound system. They're attractive. They're not going to go flying apart. And then negative 8.7 times 10 to the negative 6 joules. So potential energy of a point charge, what we just used. This is specifically the potential energy a point charge has because of another point charge. And we can, as we just did, use it for a system of charges. We just have to account for. So I guess I need to clarify that really quickly here. We were finding the potential energy of the whole system, which is why we had to account for every combination of charge. If we had only wanted the potential energy of, say, Q1, we would only need the combinations that included Q1. So coming back up here, we would have only needed these first three, because the combinations that have Q2, Q3, Q2, Q4, Q3, Q4 are part of the system, but are not directly affecting Q1. So that energy, just look at all the combinations that include the single charge that you're trying to find the energy of. So the wording of the problem will be important as well.